Hi. So in this screencast, I'm going to talk to you about the carbon cycle and how it figures into climate change. And we've talked about this a bit this year, sort of indirectly. We mostly talked about the carbon cycle earlier in the year in terms of what we call the pre-industrial carbon cycle before humans were altering it in a major way. And now that we're talking about greenhouse gases, let's just talk about how humans figure into this equation as well. Okay, so if you recall, the carbon cycle is basically how carbon, primarily in the form of carbon dioxide, moves from the atmosphere into the biosphere, into the plant matter through it gets captured through photosynthesis, and then it gets re-released through respiration. So it gets captured in photosynthesis. The carbon ends up as glucose. That glucose then gets reacted with oxygen during respiration. It returns to the atmosphere. That's why it's a cycle. So it goes into the biosphere, which includes animals that might eat it, bacteria, whatever. There's a lot of life that has carbon stored in it. It also ends up in the ocean. It diffuses into the ocean, so there's quite a bit dissolved in seawater, it turns out. And it can also end up in sedimentary rocks, in coal, oil, limestone. And so there's a bit of it that's also in these sediments, which also have a way over time of cycling and turning back into carbon dioxide in the atmosphere. So there's this big cyclical pattern. We have what's called a fast cycle, which is going into plants and animals, then back in the atmosphere. And then we have what's called the slow cycle, which takes millions of years, where it goes into sediments and then has to go through uh, uh, basically geologic processes to be released. So let's just talk about what carbon sinks are. So a carbon sink is uh, a body that contains a lot of carbon. So think of a sink as like a place where a lot of carbon is what we call sequestered or kept for a long period of time. And there's different carbon sinks or reservoirs of carbon that are important in the carbon cycle. So let's just look at the two general ways in which it flows, the fast cycle and the slow cycle. So in the fast cycle, we have the atmosphere. Clearly, there's a lot of carbon dioxide stored in the atmosphere. Uh, but also a lot of it goes into the ocean, so it diffuses into the ocean. So the ocean is a very significant reservoir, actually the largest reservoir of carbon. Soils contain a remarkable amount of it, more than the atmosphere turns out. And then there's forests and animals. So all of these are places where carbon is getting stored. So we call these carbon sinks. But we call it the fast cycle because it doesn't stay there very long. But the longest place anywhere of these things it will stay is in trees. And trees maybe live to be at on average maybe 1,000 years. So we're talking about this the fast cycle is less than 1,000 years, often significantly less, often just maybe just days or a year or two. Um, then we have what's called the slow carbon cycle. So as I said earlier, the slow carbon cycle is one that requires plate tectonics to complete the cycle. So basically, what we're talking here is uh, when trees become coal, or when plankton die and fall to the bottom and they become oil and natural gas, they'll stay there for millions of years, right? And limestone is made out of the shells of organisms. Marine organisms often use carbon dioxide that's dissolved in the water to produce their shell material, which is called calcium carbonate, which is CaCO3. So it's got carbon in it. So shell matter, coral, that all accumulates on the bottom of the ocean, and it resides there again for millions of years. So we call it the slow cycle. So basically, think of this in terms of tens to thousands of years, and this is millions to hundreds of millions of years. It turns out the ocean, not the atmosphere, but the ocean is by far the largest carbon sink there is. Has more than 50 times as much carbon dioxide in it than the atmosphere does, really closer to 60. And so basically what happens is as carbon dioxide builds up in the atmosphere, it just basically pressure pushes it into the oceans, kind of like when you're like at a movie theater, they make a carbonated beverage for you. Just atmospheric pressure is enough to push it into the water. So carbon dioxide, like many gases, is soluble in water, and so there's this process where it tends to dissolve in. Now we find is it tends to dissolve in better in cold water than it does in warm water. This is true for all gases. So gases are always more soluble in cold water than they are in warm water. Think about when we talked about thermal pollution. The problem was that oxygen doesn't stay dissolved in the water when it gets warm. Well, the same is true for carbon dioxide. But rather than think of it's true that carbon dioxide There's what we call the oceanic carbon pump, where carbon dioxide goes into the water at a high rate near the poles where the water is very cold, and then it tends to come out of it closer to the equator where the water is warm. Right? It's just cool water holds more, warm water holds less. And so there is this carbon cycle that happens that way. However, in terms of global warming, what we really need to think of is just in terms of which type of water can accommodate a higher amount of carbon dioxide. And the answer is cold water. So when water is cold, it can hold more carbon dioxide. And as humans put more carbon dioxide in the atmosphere, cold ocean can hold it a lot better than warm ocean can. And so what we find is that global warming is making the ocean warmer, which makes it harder for the carbon dioxide to go in. So when the atmosphere is cool, we put carbon dioxide, it goes into the ocean, so there's not as much carbon dioxide in the atmosphere. But there's some, and so that makes the air warmer. When the air is warmer, it makes the water warmer. When the water is warmer, it can hold less carbon dioxide, which means the concentration in the atmosphere goes up, which makes it even warmer, which makes the water even warmer, which makes it hold even less carbon dioxide, which means even more is in the atmosphere, which makes it even hotter. So we get one of those positive feedback loops. There's so many of them, and they're all bad. Okay, now the second largest, and this might surprise you, the second largest carbon sink is soils. And the reason is there's a lot of decaying plant material, or let's say there's a lot of plant material, non-living plant material that is in soil. And so it's getting consumed by, it's just sitting there, and there's a lot of it there. So think about a forest. You see all these dead leaves, dead twigs. It tends to work its way into the soil. Where that upper layer of soil has quite a bit of humus and organic material, in that A horizon and in the humus horizon. And so that represents a significant amount of the planet's carbon, second only to the ocean, and maybe 3 times more than the atmosphere itself. Now, what happens is bacteria and other decomposing organisms, beetles, worms, whatever, in the soil tend to eat this material, and as they digest it, they release carbon dioxide into the atmosphere. So it turns out that soil is actually a very major source of carbon dioxide entering our atmosphere. And you won't be surprised to learn that bacterial metabolism increases with temperature. The warmer it is, the faster bacteria multiply. That's why you keep food in the refrigerator, not on the counter, because you want to reduce the rate at which those bacteria are multiplying. Keep in mind, each bacteria is going to respire and put carbon dioxide into the atmosphere. Well, it turns out when soils get warm, those bacteria multiply faster. They're more active. They eat quicker, and they respire more, so they put more carbon dioxide in the atmosphere. So cold soil gives off a small amount of carbon dioxide. Warm soil gives off a lot. So I imagine you can see another positive feedback loop, right? So as the air gets warmer, the soil gets warmer. As the soil gets warmer, the bacteria grow faster, they respire more and add more carbon dioxide. And keep in mind, this is the second largest source of carbon dioxide on the planet, so it's significant. Now, it's worth noting that trees are a carbon sink. Forests are a major carbon sink, and the reason is they absorb carbon dioxide during photosynthesis. So here, with my lovely artwork, you have a small tree, and it's absorbing carbon dioxide. Well, as that tree gets bigger, it continues to bring in carbon dioxide. And what it's doing is, in order to get big, it basically has to make, it takes glucose and it stitches it together to make a starch-like substance called cellulose, which is what wood is. Okay, so wood is basically glucose molecules that have been rearranged and polymerized in order to give structural support to the plant. So they represent a stored sink of carbon, a reservoir of carbon. So I'm sure you're aware that forests are are responsible for holding a lot of the world's carbon, but not as much as you might have thought, right? Not as much as the ocean, not as much as the soils. So it's not moving forward. Okay, so think about this then. Well, what are the effects of deforestation? Well, deforestation means I'm chopping down these trees, and now they're not. Think about a little tiny tree, right? A brand new tree. After a year, it went from being this big to this big. Well, how much carbon did that take out of the air? Not a whole lot, right? Now, this tree here, when this tree was growing, if that tree grew this much a year, it probably grew more than that. The whole diameter of the tree got bigger. So we're talking about like lots of carbon. So big trees take up a lot of carbon as they grow. Small trees don't take up nearly as much. So when we cut down trees, we're greatly reducing the rate at which carbon is being sequestered from the atmosphere. Another thing that happens too is when we engage in deforestation practices, Not only are the trees not taking carbon dioxide, but now the soils are getting warmer, so the bacteria are becoming more active. And the other thing too is it's just that the ground can absorb more solar radiation when instead of it going into photosynthesis, it's just going to make the ground warm, and that increases Earth's energy budget as well. So deforestation, bad idea. Forest fires are even worse, and the reason is with a forest fire, you're not only getting rid of the trees, but you're also converting them back into carbon dioxide, right? So it's basically burning is the same thing as respiration. It just happens, without enzymes, and it happens at higher temperatures, but it's the exact same process. Cellulose plus oxygen makes CO2 plus H2O. And so you're basically directly releasing all that sequestered carbon. So if you think we have a forest that's been collecting carbon out of the atmosphere for thousands of years, and now we release it in one forest fire right back into the atmosphere in just a matter of minutes, hours, days, right? So forest fires are a significant source of carbon dioxide being added to the atmosphere. And again, you're not going to be surprised if you think this one through. Okay, wait a second. As the temperatures get warmer, the air can hold more moisture, so the soil and the plants, they tend to dry out. Okay, so as they dry out, basically a drought condition, right? If you've ever been in California in the summertime, it's terrifying. The whole place looks like it's just going to go up. If even like one little spark could set the whole thing up. Well, so what happens then is as the temperature goes up, forest fires become more likely because of the desiccation, drying out of the wood and the other fuel that's on the forest floor, forest litter. And so that makes forest fires happen more, which puts more carbon dioxide in the atmosphere. So yet another positive feedback loop. As you can see, positive feedback loops are what global warming is all about. And in fact, I've read recently that they think in the near future, the carbon dioxide released through positive feedback loops will exceed that released through human use of fossil fuels. So that even if we were to stop using fossil fuels and go, like, say, all nuclear, at this point, it may not make that much difference because we've established these positive feedback loops. Now, these are complex systems, so who knows? All right, so let's talk about fossil fuels. So coal, if you recall, was made, I should say, about 600 to 300 million years ago. When trees grew in swamps, they fell over, and in these swamps, there was a low oxygen, like hypoxic environment, which had a very low pH, and so most decomposing organisms just couldn't survive in there. So the carbon that was sequestered in the cellulose of that wood just stayed there. Over time, compaction and heat and pressure basically converted that into coal. Well, we're talking about that these forests were basically taking carbon dioxide out of the atmosphere for millions of years. And then it's all been all that carbon's just been sitting underground for 300 million years. And what's been happening is we've been digging it up and just burning it and putting it right back in the atmosphere quickly. So of course the world is having a hard time responding to the sudden dumping of carbon dioxide into the atmosphere. All right, so that's what this one is saying. So just remember, so what we're doing is we're taking coal, and this coal is basically has carbon that was sequestered and in a carbon sink, part of the slow carbon cycle for hundreds of millions of years. We're burning it, turning it into carbon dioxide and water, and releasing it in the atmosphere. And this really is the main reason for global warming: is that the carbon that's present in oil, which is again this sequestered, but it's from aquatic plants instead of terrestrial plants. But it's the same basic idea, right? So you had photosynthesis that happened tens of millions, hundreds of millions of years ago. It accumulated all this carbon over a long period of time, and now we're just been in the last 100 years we've released most of it. Okay, and surprise, surprise, the atmosphere is having a hard time accommodating it. Now, there's another place you might be a little bit surprised to learn where carbon can go, and that is into marine organisms that build shells or support structures. So there is, when carbon dioxide dissolves into water, organisms like, say, clams or other mollusks, corals, these adorable little planktonic phytoplankton called coccoliths, what they do is they build support structures or protective shells out of calcium carbonate, because calcium carbonate is not soluble in water. normally, okay, normal seawater. And so what happens then is that it's just a great way of precipitating out a shell material or a structural material that doesn't dissolve in seawater. But in the process of doing that, you're basically taking carbon dioxide and you're turning it into calcium carbonate. So that carbon ends up here. So this has a lot of carbon in it. This has a lot of carbon. This has a lot of carbon in it. And so there's a significant reservoir or sink of carbon is present in these materials. And when they die, they tend to form a solid mass at the bottom, which is called limestone. So this limestone, which fills up the bottom of the ocean, whether it's from reefs or the deep ocean, as these cocklets rain down to the bottom, there's just the seafloor has a lot of calcium carbonate in it. It turns into limestone, and it can sequester the carbon for billions of years. But then humans come along and say, you know what? I want to build a city. And one of the things we build cities out of is cement and concrete. And to make cement and concrete, you need to basically take limestone, calcium carbonate, CaCO3, and you need to convert it into a thing called quicklime. And the way you make quicklime is you take this limestone, you pulverize it, you heat it to about 450 degrees Celsius, which, by the way, is really hot. And then it decomposes from this into quicklime, which we want, and oh my goodness, look at that, carbon dioxide. Now, it turns out this process of making cement and concrete is responsible for about 8% of the greenhouse gas emissions on our planet. And that's pretty significant. And as more cities are being built and the human population gets bigger, it's going to be even more. And it comes from two sources, right? So the decomposition of this makes carbon dioxide, but also too, to get it this hot, how do you do that? You burn coal, all right? So we're burning fossil fuels to get this temperature. Then we're using that temperature to break apart this molecule, or this compound, I should say, to make this compound and this one right here. Now, limestone and fossil fuels, as I said, are part of the slow carbon cycle. And the reason is they tend to accumulate on the seafloor. And then what happens is over long periods of time, tens, hundreds of millions of years, they get pushed down trenches, these subduction zones. Remember, they heat up and they melt. And when they melt, they come to the surface, and that carbon dioxide becomes separated from either the limestone, the calcium carbonate, or from the coal, or from the oil and natural gas. And it tends to come out of volcanoes as carbon dioxide completely. So it came in here hundreds of millions of years ago, got turned into either oil or into limestone. And over the slow movement of these plates, eventually it went down here and melted, and hundreds of millions of years later, it comes back up as carbon dioxide. No wonder it's called the slow cycle. Well, thanks for watching. Let me see. All right, turn it off, Samson. How do you turn it off, Samson? There it is.